The first section in Chapter 4 is on antiderivatives. Another name for antiderivatives is indefinite integrals, so I'll be using both terms interchangeably. To give you an idea of what we'll be looking at, think about this problem. Can you find a function y such that the derivative of y with respect to x is equal to 6x to the fifth? So notice that unlike what we were doing in previous chapters, instead of my giving you the function and asking you to find the derivative, I'm giving you the derivative and asking you to find the function. Well, the answer is sure. One that you might be thinking about is x to the sixth, because the derivative of x to the sixth is indeed 6x to the fifth. Turns out that's not the only possibility, though. Another function that would also work, in other words, another function whose derivative is 6x to the fifth, is y equals x to the sixth plus 12. Because if you differentiate x to the sixth plus 12, you get 6x to the fifth, and the derivative of 12 is 0. And now you can guess that there would be lots of other possibilities. X to the sixth minus 11, for example, would be another one which worked. So each of these is called an antiderivative of 6x to the fifth. So notice that we're using the article and rather than the. We don't say the antiderivative necessarily, since there are lots of different possibilities. Each one is just one of many. So that leads to this definition. We say that the function big F of x is an antiderivative of little f of x if the derivative of big F is equal to little f. Now here's a theorem about antiderivatives. And that's that if you have any two antiderivatives of the same function, then they differ by a constant. So let's see if we can write that down. If big F of x and big G of x are both antiderivatives of the same function, little f of x, then those two functions differ by some constant. In other words, f of x is going to be g of x plus some constant. Now, I'm not going to prove this to you, but just to give you an idea, I'll let you know that the proof involves Rolle's theorem. So when I taught Rolle's theorem, I mentioned that Rolle's theorem is mostly used for theoretical purposes, and this is a place where it is used. So if we come back to a problem like this, and I say, find an antiderivative of x cubed. In other words, I want you to find some function whose derivative is x cubed. Let's think about that. When I differentiate using the power rule, I have to subtract 1 from the exponent. So that must mean that my antiderivative is going to involve an x to the 4th. But when I differentiate x to the 4th, I get 4x cubed instead of 1x cubed. So let me put a 1/4 in front. Let's check that. What is the derivative of 1/4 x cubed? The 4 times the 4th is 1, and subtracting 1 from the exponent, I do get x cubed. That worked out. Now what we're going to do, though, is I'm going to write plus c here to indicate that if I add any constant on, that will also count as an antiderivative. Now when we add on the plus c to indicate that we've got all the antiderivatives, sometimes we will call this the antiderivative. Notice, though, that when I say the antiderivative, this doesn't actually represent exactly one function. It represents a whole family of functions where c could be any number at all.